Alright, this is lesson 7.4. We're going to be talking about logarithmic functions today. This is a review lesson for those of you who've taken Pre-Calc 12 before. So I hope this won't be something that you'll have to spend too much time on. We earlier talked about one-on-one functions, right? Or one-to-one functions. They are continuous and increasing. And that exponential function that we've been dealing with, definitely one-to-one. So if it's a one-to-one, then it must have an inverse. But if I actually were to switch the x and y's, you get something that looks like this. X equals to e to the y. And it's pretty difficult to isolate the new y value by using some algebraic methods. So we define the inverse for the function f of x equals to e to the x as something different. And if you remember from Pre-Calc 12, you bet, it's the natural logarithmic function, or the natural log, or ln. Here we go, ln. So, x equals to e to the y, and y equals ln x are equivalent. And, in general, if you have an exponential function, a to the power x, then the inverse is just log base a to the power x. Okay, and notice the inverse graph is the one that is reflected in the line y equals x. And so our natural log graph looks like this. And key characteristics, you bet, goes through 1, 0. It's always increasing. And we have a vertical asymptote at, of course, x equal to 0. And that's kind of the stuff that's summarized in here. So, I hope you already know these things, and I hope this is just a review. I'm going to move on, but once again, I would like you to look at these graphical characteristics of log, and of course go back to our lesson 7.1 and compare them with the characteristics of the exponential. And I hope you find a connection, and the connection, of course, is that they are inverse functions. So, let's look at example number 1. I'm going to ask us to use a calculator to graph both y equals ln x and y equals log x on the same coordinate plane. And by the way, if you're not too sure or don't remember, this y equals to log x, that's actually the log base 10x. It's the common logarithm. And if you were to take out your graphing calculator, here's mine, you should be able to see the two different functions and be able to graph the two on the same grid. So let me erase all this stuff. Here we go. We'll take ln x, do that first. We'll do log x, that's the second one. I'm going to ask us just to use the standard window, and let's see what we get. Yes. Oh. So it seems as though you've got this one, ln, and then you also have this one, log base 10. Of course, base 10, I guess here we have the point 10, 1. And then for ln, we have here the point e, which is about 2.718, right? 1. All right. Similarities, I hope you do. Okay, both of course have a vertical asymptote at x equal to 0. Both are increasing functions. Both pass through the coordinate 1, 0. All those characteristics from above. Alright? So looking at example number 2 now without the calculator, can you use also things you've learned from Pre-Calculus 12, the transformations unit, to sketch a graph of this? Y equals to the natural log of x minus 2, all with the absolute value. So I, of course, like to compare with something that we know, and I hope you know what the ln graph looks like, because I just drew it above. If I were to make this change, and change the x to x minus 2, how does that affect the function? Hopefully you remember that this, of course, is a transformation 2 to the right. So I can automatically say, oh, my absolute value, my asymptote is now 2 units to the right. That point 1, 0 is now at 3, 0, and I can just quickly graph this out. Beautiful. And there's my graph y equals to the natural log of x minus 2. But we're not done, because I'm asking you to take the absolute value of this function. And what does the absolute value do? Yes, it makes everything that is negative. So every negative y value becomes what? Positive. So this part of the graph here disappears and gets reflected up top. And now we have our graph of the absolute value of natural log of x minus 2. Ta-da! Okay, so on to the next page. Hopefully you also remember how to change back from the exponential form to the logarithmic form. And I hope you remember this thing here is equivalent to this thing here. Just different ways of writing the same thing. Generalized to any base of a, you have any log base here too. Okay? So hopefully we can just quickly do these examples as a quick review. Can you actually change the following exponential equations to logarithmic kind of equations? So the idea, of course, is that the logarithm is always an exponent. So I look at the exponent of 4 and I say 4 is equal to, in this case, log, and what's that small little a? That's the base. In this case, the base is the number 3, and the result is 81. So 4 equals to log of base 3, the number 81. For part B, the exponent once again is 0, so I'll say 0 equals to, I guess it's log base e to the power, or not to the power, to the log base e of 1. Log base e, of course, can be written as the natural log. So 0 equals to the natural log of 1. And then also the last one here, we have log without a base, so we know that's base 10 is the common logarithm. And in this case, our exponent is, oh wait a minute, this is the other form. So now, this is the logarithmic form, and I want you to change it to the exponential form. So like I said, the base is 10, so 10 to the power of, and yes, the logarithm is an exponent, so here's your exponent, -1, and the result is the number 0.1, which of course equals to 1/10. Okay? Now, in example number 4, since e to the power of 0 equals to 1, we got that from part B in example 3, then of course natural log of 1 equals 0. An important point to know. And of course, since e to the power 1 is e, then the natural log of e is also equal to 1. Also an important point to know. And more importantly, because the natural log and the exponential function are inverses, ln e to the n, or e ln n, two functions that are inverses put back to back, just give you what you originally started with, and that would be n. So using this idea now, can you complete the examples in number 5? I'll let you try that yourself, and I'll just keep quiet, and come back and check your answers with me when you're done. Remember, common logarithms, 10 to the power of log base 10. Okay, I hope you got those answers. If you did, give yourself a pat on the back. We'll move on to some properties of logarithms that you should have also learned in Pre-Calc 12. Hopefully you remember that natural log, or any log of two numbers multiplied together, just can be split up into two separate logs that are added together. Division, of course, becomes subtraction. And this funky one where you have the exponent, that exponent gets brought down to the front and it becomes multiplication. So understanding these, let's quickly do examples 6 and 7. So now I want you to expand this. You see division, so this just equals to the natural log of 5 minus the natural log of 8. Part B, I'd suggest that you rewrite that cube root as a power first. Noticing it's a power, now we can bring the power down to the front. Natural log of x squared plus 1. Now don't be tempted to do the following. Distribute the ln to give you ln x squared plus ln 1. No such thing as a distribution of a function. Okay? And once again, this is not multiplication of two things. So you cannot separate it into the ln of two things. Don't do that. This is it. We're done. Condensing to a single logarithm. Be careful with these coefficients in front. You cannot condense them yet until they are removed. So I would say let's rewrite that as ln x to the negative 3 plus ln y to the power 5. And now once we have this ln of something plus ln of something, we can combine them together by multiplying those two things. And that would be fine. If you like positive exponents, then this is also fine. I'm going pretty quick here because I think this is a review, and if it's not, then you can look at my videos from Pre-Calc 12 series. I think this is Unit 8 in the Pre-Calc 12 series of notes. Okay. Part B here, once again, that 1/2, let's make it an exponent. That 3, I'll make it an exponent as well. I see the first two as an addition, so that can be combined together to become multiplication. Ooh, I see a subtraction that can be combined to become a division. And we're done. Cool. Nice. Alright, next page. Boom. Here I'm going to help you review how to solve equations. So in this case for 8a, can you solve for x? Well, the idea is, of course, is to isolate x. And to do that, I would suggest that you subtract 6 on both sides first. The hard part about x in this question is that it's a or an exponent. And so how can I bring the x down to the front? Well, the only way you can do this is by taking, in this case, natural log. Because the natural log of e, well, we told you earlier, those two functions back to back just leave you with the 2x minus 5. And I'll just leave this as natural log of y minus 6. And then we'll just perform more algebraic steps to solve. I'll add 5. And then also divide by 2. And I'll do this in one step because I'm running out of space. And that would be my answer for x. Okay. Once again, do not distribute the ln. Okay. Don't do that kind of stuff. Oops. Don't do that. No. Alright. How about part B? I see we can use those log rules. I hope you can see that too. Subtraction, of course, means we divide. So we have x over x minus 8. And that equals to 3. Now at this point in time, there's a few ways you can do this. Some of you may be thinking, I have to get rid of that log. So how do I undo the log? Well, you undo the log by applying the inverse. So what's the inverse of log base 2? Yes, it's 2 to the power on both sides. So if you do that, the 2 and log base 2 kind of cancel each other out. And you're left with x over x minus 8 equals to 2 to the power 3, which is 8. Nice. Now, if you didn't like that, I'm going to erase that right now. You don't have to if you don't want to. But if you didn't like that, the other way you could have done this is, hey, this is logarithmic form. Can you change this into exponential form? Well, exponential form says the base is 2, the exponent is 3, and the result is x over x minus 8. Well, 2 to the power 3 is equal to 8. 8 equals to x over x minus 8. Well, that's the exact same thing that we wrote down previously. So both ways work. And now from here, can you solve? Well, I would probably just cross multiply. So 8 bracket x minus 8 close bracket equals to x times 1. And we'll just do some algebraic manipulation here. We'll subtract x on both sides. We'll move the 64 negative from the left side to the right side. And we'll get the answer 64 over 7. Alright? So I hope that's a good review of how to solve these logarithmic equations. And once again, if you're having trouble with this stuff, go back and review Pre-Calc 12, Chapter 8. Oh, a few more things. The change of base formula. Yes, on your calculator, unfortunately, there is only the log key, which is base 10, and the ln key, which is base e. And if you've got weird bases, then the only way you can do it is by using this change of base formula. So log base ax is equal to log x over log a, or you can also use ln x over ln a. Either or, it doesn't matter. So for number 9, you can rewrite this as log 112 over log 7 using the common base of 10. Or you could have also used natural log of 112 over natural log of 7. And in both of these cases, you should get the same decimal answer. You don't believe me? Let me show you. Clear, clear, clear. So we'll take log 112 divided by log 7. There you go, 2.4248, blah, blah, blah. And I can also take ln of 112 divided by ln of 7. And you'll get the same answer, 2.425. Okay. So now, if I ask you to find an exact value to solving this question, how would you solve this exponential question? I think in Pre-Calc 12 you were probably told to take log on both sides, so you can do that definitely. And then what happens is that the x plus 2 gets brought down to the front. That's all multiplied by log 3. That equals to log 6. You want to solve for x plus 2, so you'd probably isolate that by dividing both sides by log 3. And then subtracting 2. Log base 6 over log 3 minus 2. Now, by the way, the log 6 over log 3, we had to change the base formula, is actually this. Log base 3, 6 minus 2. Oops. Okay. Using your calculator to find the decimal equivalent, well, then you probably don't want to use this form because you don't have a log base 3 key. But once again, this might be a little bit nicer way of writing it in exact value form. I'd probably take this expression and then plug it into the calculator to evaluate. Log 6 log 3 minus 2, voila, negative 0.369. Alright, so I hope this was a good review of logarithms. Guess what we're going to do next with logarithms? Take the derivative. And do you know what we'll do after that? Integrate. So stay tuned for those. This is the precursor to it. As an assignment, you can probably do any of the questions from 1 to 40, but I'll make this whole thing optional for you. Okay? Because if you really feel like you have a good grasp of all this stuff, then don't do any of it. If you feel like, hey, I just want to do a quick review, then perhaps just do all the odd numbers. And if you need more practice, yeah, do more than the odd numbers. Alright? So I'll leave it up to you. It's choose your own adventure.